Hello everyone, welcome back to my YouTube channel. So today we will be going through a paper that's all about trying to combine the knowledge of LLMs and the knowledge from graph neural networks and see how we can perform knowledge distillation in order to create a better, accurate model from them. So let's get right into it, shall we? From what we can see right here, the paper that we will be going through is titled Large Language Model Meets Graph Neural Network in Knowledge Distillation. Well, there's really three components here, like I say, LLMs and GNN and knowledge distillation. And I'm covering this paper partly because of my PhD research work. So let's take a look at the introduction, shall we? So it says, recent advancements in using LLMs for text attributed graphs, TAGs, learning have shown significant potential, but its practical deployment is often hindered by substantial computation and storage demands. So what they are saying here is that it is really beneficial to use LLMs to process text attributed graphs. And if you don't know what text attributed graph means, if I'm not mistaken, it is something like this. So basically, in a graph, you have nodes and edges, right? And the edges connect each nodes, and what you will have is each node having its own text that's labeled into it, right? So you can kind of imagine the text being the information about the node that's in it. So let's go back to the abstract. Okay, so what they're saying is that doing this kind of approach is great, but it's computationally and storage demanding. And conventional graph neural networks, yeah, I would assume you all know what graph neural networks is, but if you don't know, it's basically just a type of neural network that takes in an input of a graph and process it into a prediction output of some kind, any kind, really, right? So, but here's the thing, right? Graph neural networks are more efficient, but they struggle with the intricate semantics embedded in the text attributed graphs. So here's what it's saying, right? So the LLMs is quite accurate for text attributed graphs, but graph neural networks, on the other hand, is not that great with TAG. So what I want to do is to combine the understanding of LLMs with the efficiency of graph neural networks. So what they're going to do is to do some kind of a knowledge distillation between the LLM and the GNN. And they call it linguistic graph knowledge distillation, LinguGKD, but we're just gonna call it knowledge distillation from now on. And yeah, and it uses the graph oriented structure instruction tuning to train the pre-trained LLMs as the teachers. So what you basically do is that you perform supervised fine tuning onto the pre-trained LLMs like your typical Llama 3 models, and you use that as the teacher component in your knowledge distillation framework. And also introduce a layer adaptive contrastive distillation strategy, and we will see what they meant by this in a second. So that they can align the node features between the teacher LLMs and the student GNN. Like I predicted, it's all about getting the information from the LLM into the GNN, as so that you can have both accurate and efficient model, right? Okay, and this helps to transfer the semantic and complex relational understanding from the LLMs to the GNN, and they perform a lot of experiments on different data sets, and it shows that this approach enhances the prediction accuracy of GNNs without additional uh, computational costs. So, all right. And if they when they compare it to the teacher LLMs themselves, GNNs are offer greater speed, and the accuracy I would assume it's going to be a bit lower, but it really depends. Like I've seen some cases where if you perform knowledge distillation, even on some models, it can get much better than the teacher itself. So it's really hard to tell, but let's see what the paper has to offer here. All right. So once we know the abstract, now let's take a look at the introduction. So uh, pretty much it's the same thing, you know. So TAGs integrate structured graphs with text information, like I say. So blah blah blah, and I mentioned about different LLMs bringing in new capabilities for TAGs, and they also mentioned how they are good at reasoning for some complex tasks, but it's not great for every single cases, right? And that's obvious. And there are a few studies that show that if you combine knowledge graphs, then you can make the LLMs essentially not hallucinate that much, right? Okay, and also talk about like graph neural networks are really good at interpreting what kind of graphs they are, but it struggles in understanding the graph relation themselves in terms of semantics. So right here, all right. So GNNs, it doesn't work that well if you have textual graph data, whereas LLMs are pretty good with semantics and contextual understanding, but it's really expensive. All right, so that's pretty much what the abstract said before, and I also talk about some recent advancements in this kind of a problem and how they're trying to solve it. Firstly, they have the approach of LLM as enhancer and LLM as predictor. So the LLM as enhancer, what they basically do is try to enhance the node embeddings in the GNNs by using the semantic processing capabilities of the LLMs to in order to make the GNN understand the semantics of the text attributed graphs better, right? On the other hand, LLM as predictor approaches, they use the LLMs directly for prediction tasks. Um, I think it's without the graph neural network. I think so. What they basically do is just taking the entire graph structure and feeding it into the LM and ask it to make the prediction directly. So that's that. Let's see what I have to say. Adapting transformer models to incorporate graph structures or by encoding graph data in natural language. Yep, that pretty much is it. But the accuracy can be questionable at, at times. Yeah. And these works show that the potential to use LMs as a foundational model for graph learning, but it's quite huge. It's like billions of parameters, and yeah, it's really impossible unless you have like a lot of GPUs. But in this case, right, they want to utilize LLMs just to boost the accuracy of GNNs, right? And they talk about knowledge distillation being promising, blah blah blah. So, and that's not really important because we already covered that. All right, right. Obviously, the challenge is, right, if you're trying to combine LLMs and GNNs, LLMs are great for text data, while GNNs are evolved to process graph data. Both these two types of data are different, are really, really different. So it will be interesting to see how they can somehow unify these two things together. So it's about this then. All right, and then propose their approach, their knowledge distillation approach. Right. So let's see about this. So yeah, they're pretty much mentioning the exact same thing from their abstract, which is not that interesting. All right, let's see. So I think we're equipped with the necessary knowledge to get into the paper. So let's go to the conclusion first before anything else, and see if they mention anything new. So blah 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 blah. So here's the conclusion. Yeah, and it pretty much says that yeah, so their approach enhances the prediction accuracy and convergence rate of GNNs just by doing this kind of knowledge distillation strategy. So that's pretty much that. But the more interesting thing would be their methods, right? So let's take a look at their method for a second. Okay, let's start off with the preliminaries. Okay, definition one, text. So they define what a text attributed graph is. They stated it here formally, but I pretty much just explain it verbally, informally. Huh? So, okay, right. A graph is denoted as that, where you have the nodes, and the edges, and you have the node attributes with xi being the text embedded into each node, and that's pretty much it. And now, defining graph neural networks. Yeah, so while this formula might look complicated to outsiders, right? But what it essentially is, right? If you think about it, right? If you know a transformer model, right? It's basically kind of similar in the sense that it's kind of like the attention mechanism where you get the relational data, right, from a single token with respect to other tokens, right? It's pretty much the same thing. And basically, if we take a look at it as a single black box, right, you essentially have your input embeddings into the GNN layer, and out you will have another embedding, right? And you would perform this kind of a convolution operation over every single nodes in the graph. So that's a high level summary of graph neural networks. It's not precisely accurate, but I think that's enough for this paper. So okay, right, and now let's go to here. So, okay, and then define how they conduct their knowledge distillation approach in definition 3. So, okay, LLM to GNN knowledge distillation can be formulated as a quintuple, right? Having MT being the teacher model fine-tuned on the graph for generative graph inferencing, and MS being the student GNN model, for discriminative tasks, and F representing the knowledge to be transferred from the teacher to the student with the distillation scheme S, which is learned by extraction algorithm. Okay, so that's a lot of things to cover here. So what it basically is, right? If we take a look at let's see, yeah. So if we just do this, right? So if we take a look at the equations, it might say something about it. But let's actually take a look at section 3 for now. So, okay, figure 1 illustrates their framework for their work. So, so the highlighted 3 components, the teacher feature learning by the LM, the student learning, and the layer adaptive contrastive distillation loss between the two feature sets. Okay, so just in case, right? You see the layer adaptive contrastive distillation loss. It's actually referring to equation 3 right here. But you have the feature from the student FS, and you have the feature from the teacher, and you try to minimize their differences. So that's that. But let's see right here, and yeah, so that's pretty much that. So if we take a look at let's see, crucial we the blah blah blah. Okay, so let's see if we can understand figure 1 directly. So figure 1 propose knowledge distillation framework, includes 3 main components: teacher learning, okay, student learning, and layer adaptive distillation for both models. The lower left section depicts the process of describing the structure of a graph done with tailored graph instruction prompts for the teacher to learn. So what this basically is that you have a graph, right? And you feed it into the student and the teacher, right? So feeding it into the student, it's pretty simple. You just treat each node having its own embedding, and then you feed it into the GNN layers, and that will give you a set of features about the graph from each layer. So, but if you take a look at the LLM, it's not that simple. What they have to do in this case is that they will need to pass it into a graph instruction prompt encoder right there, and and it has to go through a instruction encoder, a structure encoder, and a query encoder. And after that, we have to concatenate all those features together from each encoder to create a P tensor, I think. And then you feed in those tensors into a multi-hop feature extractor of the graph LLM. And then after that, you get each hidden embeddings from each layer, right? And then they go through a set of knowledge filters. They call it that way. I'm not too sure yet, but we shall go through that later, right? And then once you have your complete set of H tensors, you basically just perform knowledge contrastive layer adaptive knowledge distillation in this part in order to get your knowledge distillation loss term, which you can obviously incorporate with your training objective function. So that's the high level view that I can come up with. But let's see what they have to say even more. So given a graph with a center node vi and a specific neighbor hop k, we can obtain a collection of neighbor subgraphs from structural free up to k hopped, where gki equals to this tuple denotes the k hop subgraph. So basically, a subgraph, in this case, a k-hop subgraph, is something like this. So let's say if you have the center node here, you assign that to be the center node. What it means by a k subgraph is that, if you have a hop subgraph, it would basically mean the immediate neighbor, right, which you can jump by one hop. And this 5-node subgraph would be the one hop subgraph with respect to the center node. And what they're trying to do here, from what I can read, is that it is trying to get the k-hop subgraph neighbors of the center node, right? And what is it trying to do? Is it trying to process it using the LLM directly? Okay, let's see. To enable the LLM to understand graphs, they need to craft. Okay, so let's see. Okay, right. So structure free up. Okay, right. We obtain a collection of neighbor subgraphs. Okay, right. So they obtain the subgraphs, and then they define a specific instruction prompt, right, called PK, and it contains 3 different types of components. Task-specific instructions that delineate the expected model action, the structural prompt, that is the natural language description of the subgraph. Okay, I see. So, okay, and the task relevant query. All right, I think I kind of understand it now. So what they're basically saying is that they're essentially taking each subgraph and trying to get the LM to understand it and create a description from it. Got it. So yeah, and then basically concatenate everything into and make PK, right? So, and interestingly, they say that they employ node classification as a side task to enable the LM to comprehend graphs. So they use so they instruct the LM. So basically, they kind of like fine-tune the LLM to perform classifying the attributes of the nodes as a classification task. And we've seen these tasks before in graph neural network learning. So they are just bringing in a different training objective from the graph to the LLMs. Now, in alignment with OpenAI's prompt engineering principles, okay, I'm going to check that one out. We carefully design I and Q. So I being the task-specific instruction, right, and task-relevant query, which is Q. So basically, it's the task instruction and it's the question, right? So that's. So they propose 2 types of prompts, right? So this one is the instruction. Basically, it says implementing a node classification system for a type of graph representing the nodes as this, and this. Classify nodes into list of classification categories based on attributes and link relations. Classification criteria for a specific graph. And that's the instruction that you're going to give to, let's say, a Llama tree model. And after that, the second prompt, node classification query, asking the model what category should a, a node in the graph, right? A node in the graph be classified as. So that's the question right there. So in these templates, each node is represented by a tuple that encapsulates the node's ID, degree, and the corresponding textual attributes. The placeholders with curly brackets can be filled with the specific graph data. Yep. Okay. All right. So denoting additional optional prior knowledge to help the LLM to generate labels for the center node. But I'm not so sure what the labels are in this case. But let's read more. Okay, so so there are some additional tricks to craft the structural prompt. So they prioritize key elements such as node textual attributes. Wait, just give me a second here. Okay, anyway, node degrees and multi-order neighbor interactions. Right, with conventional multi-layer GNNs, referring to the strategies from that, we develop a linguistic structure encoder, FE, that transforms it into a natural language description. Yeah, I can already tell you that this encoder thing, this like generating the text description of the graph is gonna be pretty difficult, and it's gonna be pretty expensive. Because that's the thing that I'm doing right now. It's taking such a long time, but yeah, let's see. Problem number 3. Okay, right. Structure information, right? Intermediate paths, k-hop neighbors, blah blah blah. Okay, and the k-hop neighbors represent the ensemble of neighbors reachable at k-hop. Okay, so that's the specific details we can create for every single graph. Okay, right. And let's say this a structural prompt for every single graph, for every single subgraph. Sorry. Notably, when layer equals to 0, focuses on the node textual attributes. Yeah, obviously, right. So this iterative structural prompt changes the relational dynamics, going from its a single node and up to its k-hop neighbors in the graph. So by concatenating those, we get a graph instruction prompts. All right. And now here comes the fun part. Then they do supervise instruction fine-tuning to make sure that the language models can do the task. So let's see right here. So each prompt PL is utilized to directly fine-tune the language model to generate semantic category YI. Okay. So this is the label. This one right here, the semantic category YI. Have we seen? Yeah. Have we talked about this? YI? Have we? Because I'm curious. I can't see it. I don't think so. All right, fine. Okay, right. Generate for the center atom without any modification to the tokenizer and vocabulary of the language model, and they use a negative log likelihood loss as their objective function. All right, fair enough. Okay, where yj corresponds to the j token that the LLM generated for the node label. All right, so that performs this fine-tuning for the node classification task. And voila, this is the endpoint. We get the fine-tuned LLM as the teacher model. All right, cool. And now it's getting even more exciting because we can use this LLM teacher model for the GNN. All right, but before that, let's see how many more steps do we need. So, all right, I see. So two more steps. All right, cool. I think we can finish this one a bit early. All right, so the key components of the framework, blah, blah. Okay, let's see right here. Let's get to the interesting part, the juicy part. All right, okay. So the first, use the fine-tuned LLM, the teacher model, right? By doing this, I think. Okay, building insights from that. They observe that the instruction significantly enhances the LM's proficiency in creating semantic features. Cool. Consequently, they use the entire prompt set for extracting node semantic features rather than limiting it to the structural prompt set. Given the LMs use the transformer architecture, right? We extract the node semantic features as follows. Okay, so this is how they're extracted. For an instruction prompt, PL, they process the sequence of tokens with this, which I think we all know what that means. This is the prompt. This is the weights of the layer of the neural network, and the neural network is the embedding neural network. Yeah, it's the embedding layer of the LLM. You get this EL, and the EL is fed into the transformer module, right? And that's how it works. So, and they also consider the feature of the last token, P sub PL, right? Yeah. So here, this this feature of the last token, right here, it has the aggregated contextual information of the entire instruction prompt, right? So it has the details about its k-hop neighbors and its own attribute data. So this thing right here, I think, is what's going to be useful, because if we take a look back into the figure, it does use it. It does, right? In this case, right? In this part right here, before it goes through knowledge filters. Now this part is straightforward. So for distilling knowledge from teacher, we then process each elf order feature through a specialized hop specific neural knowledge filter. You know, they just call it a specialized hop specific neural knowledge filter, and MLF, which is good in filtering layer knowledge. So what it basically is a neural network that takes in, why do they call it a filter? Just call it a neural network. It's basically just a linear neural network followed by a activation function, and after that you apply a layer norm. Okay, I don't see how this is like that's special enough to call it a filter. Maybe I could be wrong, but let's see. All right. All right. To align the node features from different hops into the same lower dimensional distillation vector space, right, without altering their distribution. A cross-hop shared linear feature projector MP is designed to restructure these features. So they also have this NP function right here, this pro projector, right? So this projector is basically just another linear neural network. All right, it's not that interesting, honestly. Okay, where there's adapted poses subsequent are trainable parameters. Yep, okay, that's fine. Applying this process across all subgraph orders up to k, they obtain a set of teacher node features ft, yep, just like in the figure, or htl, right? And we can use that. But let's read through the second part right here, student feature learning with GNNs. All right, then they use the GNN to extract the multi-hop node features as shown in figure 1. Yeah, so the GNN can be any kind of GNNs, whether it be GCN, graph convolutional network, GAT, graph attention network, graph attention network, yeah. And there's a lot of different variations, but they're pretty much just graph neural networks, essentially. So, all right, I don't need to go through that because I already covered GNNs a bit just now. All right, but what's interesting here is that if we take a look at this part right here, this embedding G. So, all right, let's read this part. So for a given k-hop neighbor subgraph GIK of a center node, the k-order message aggregation process in graph neural network unfolds as follows. So the embeddings, the message passing, and then updating the nodes in equation 7. Okay, embedding G is the text embedding model of MS, right? So you can use something like bag of words, TF-IDF, which is pretty standard in NLP, right? To convert the text data of each node into a smaller dimensional vector, right? So that's that. Not too interesting, right? Okay. So subsequently, they synchronize the node features into distillation vector space using a normalization layer. Yeah, so they perform some kind of a normalization in order to make it compatible with the teacher features, I think. So yep, and that's that. And you can get the student features with in this term. And okay, right. And now this is all what we have been waiting for, right? We have prepared the teacher features and the student features, and now we're going to do some knowledge distillation in between those two. So layer adaptive contrastive distillation, right? So, okay, so here's what they have to say. The relevance of node features varies significantly with the order of their neighbors. Structural free features highlight a node's core features, right? Lower order features cares about the intermediate, cares about the immediate interactions, and as you get higher and higher, it covers a lot more parts of the entire graph. So it's essentially from local to global information extraction. So, okay, that's great. But different tasks, right, requires different orders of features, right? Some needs more specific local information, while others requires global information. right? So, and they argue that a one-size-fits-all distribution approach doesn't really work, right? So, and they say to fully leverage the teacher LLM, right? They propose this new approach, this contrastive distillation approach. So this approach, right, tailors the distillation to the importance of the node features at each hop, right? So, okay, right. Tailors the distillation process to the importance of the node features at each hop. Okay, so to better capture the local and global structure. All right, but we shall see the results whether or not actually gonna work that well. But okay, blah 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 blah. Okay, so then talk about some approaches, right? Such as a contrastive learning with info NCE loss. Basically, what it does is that it tries to separate out similar and dissimilar pairs of features and then see whether or not you can see what is similar and what is not, right? So, and that's basically contrastive learning essentially. So, so here's what they do. For each node and its corresponding alpha order feature, the positive sample is, okay, right? So hear me out. The positive sample is the same nodes feature learned by both the LLM and the GNN. So let's see. So we want this, let's say, let's give it color blue. Now this is from the GNN and this is from the LLM, right? It's about the same thing but produced by two different models, right? So you want this to be as close as possible. All right. And as for the negative samples, it would be like trying to compare it against some like other nodes, right? Other nodes. Okay, so it's features of nodes from different categories compared to the center node, right? And you're trying to keep it far away. And this selection helps in maintaining a clear distinction between different classes, therefore improving the classification accuracy of student GNN. Formally, given a node, its L order feature from the LM and the student can be defined as this. Okay, so what you're gonna do right here is pretty simple. So right here, let me draw it. Let's say this red ball right here. This is from LM, but it's essentially different information. So if I just write the information tag right here, this represents 1, this is 1, but this is 2. So you're just trying to keep the dissimilar things out of the way, right? So, okay, and you have some kind of a loss term, a contrastive loss term, in this case, adjustable with a parameter, a temperature parameter, right? And then say that out loud. Oh yeah, in this case, since it's contrastive learning, right? The issue with contrastive learning in this case is that it depends on the batch size. So, from what I still can remember back like a few years ago, there's a problem with it is that you need to have like a sufficient number of samples in your batch. Otherwise, this approach doesn't really work that well. So, maybe they will say about that. But yeah. So recognizing the unique importance of different order neighborhood structures in various downstream tasks, we introduce a distillation factor, right? Okay, blah blah blah. Okay, for each distillation loss, which allows to adaptively focus on the layers that are more critical for the specific task at hand. Right. So let's say if you're doing some kind of a graph classification and you want to use this approach. So what you would do is that you would have your I don't know, classification, right? And you would have this knowledge distillation term right here, and it will have a trainable parameter, right, between each distillation loss term. So yeah, that's that. That ensures balance of whatever. All right. And okay, and then describe what kind of data they're going to use. It's not much, but it's still. I mean, it's all right. Just Cora, PubNet, and archive graphs. I mean, that's pretty much standard. Okay, so model training. Um, okay, so the model training. I don't think it's gonna be that. Yeah, yeah. So this is the loss objective function here. Just combining your graph classification problem with your KD loss term right here, and you can change alpha and beta. Typically, what I would do is to set it to like 1 times 10 to the power of -5, just to start off from really low and then see if you get any benefits as you increase it further. So, all right. Yeah, so there's nothing much to that. Well, how about if we just take a look at the results already? Don't need to drag this out any further. Let's see. So their approach, okay, where is it? Where is it? The prefix. Right. Where's that thing though? Okay, right. I see it now. So let's see. So let's say we take a look at a llama tree because the llama tree is newer, right? Oh, and it pretty much won the entire way. You know what? That's pretty good. That is pretty good. So yeah, I have nothing to say other than it's pretty good for what task is this? This is a, oh yeah, you're right. It's Cora, PubNet, and Archive. So yeah, so as you can see, if we take a look at the training curve, right? It's not really that special. Let's see, there's, right, that's that. And then there's a talk about some other things as well, but it's not that interesting for now. I might have a look at it later, but not now. Oh yes, here it is. Yes, the hyperparameter search. Now this is interesting right here. So if we go from 0 hop, which is basically the center node, and as we increase the number of hops, you will see that the accuracy increase initially, and then it remains kind of equivalent after that, or maybe even drop or increase a bit, but it generally goes down as you increase to a lot of hops. Well, typically the problem with this is that graph in general, graph dealing with graphs is a pain. due to the effect called over smoothing. Basically, every single features becomes the same after you apply the operations to each one of them. Yeah, so everything converges to the same representation, which really makes the accuracy goes down by a lot. So yeah, but let's see for a second here. Okay, right. So and the same thing happens for the F1 score as well. And here they show that it is important to get your feature dimensions up to a certain point, but after that, after this threshold is basically equivalent. So yeah, so that's what they show. Really interesting, right? Yeah, and that's all for this paper. Yeah, I hope you guys will like it. Yeah. So all right, I hope you guys will like it. And make sure to like, comment, and subscribe if you found this video to be useful. But yeah, and don't forget to let me know what kind of papers you want me to cover with you guys in the next couple of videos. I will be going through some other papers as well pertaining to graph neural networks alongside with large language models. And I'm doing this not just for YouTube, but also for my PhD as well as I'm working in this area as well. So yeah, thanks for checking in, and I hope you all stay awesome. Bye.